This problem from the Hibbeler book says that marbles having a mass of 5 grams are dropped from rest at A through the smooth glass tube and accumulate in the can at C. We want to find the placement R of the can from the end of the tube and the speed at which the marbles fall into the can. And we don't really care about the size of the can that they're falling into. All right, so when I look at this problem, if I were to get this on a quiz or something, I would automatically notice we've got a change in elevation, right? Change in height, because we're dropping from A to C. And that would tell me that I would probably want to use work energy. So that's what I'm going to use here. I'm going to use potential energy to solve this problem. And remember, our equation for that is going to be U equals delta T plus delta Vg plus delta Ve. So that's the generic equation that they have in the Hibbeler textbook. Now, if we look at this, U, remember on the left side here, this is for forces that do work. All right, so any forces other than springs and gravity would go over here. I don't really have anything else in here that would do work because this is a smooth tube, it says, right? So there's no friction there. Nothing else is doing work. That means this goes to 0. Then we've got delta T, that's change in kinetic energy. So if we have a change in speed, we're going to have that term, so that stays. We have potential energy due to gravity. We've got that because we've got this elevation change. And then the last one, delta VE, that's elastic potential energy. I don't have a spring, I don't have like a rubber band, I don't have anything like that, so this is going to go away. That leaves us with our delta T plus delta VG. So let's go ahead and figure out what those would be. So first of all, delta T, that's 1/2 times the mass times your final velocity, which in this case would be the velocity at point C, so right here, and then minus our initial velocity, which would be the velocity up here at A. Whoops. So we need to figure out what that should be. So if we look here, what do we think we're going to get? Well, we're going to have 1/2. The mass is 5 grams. I want it in kilograms, so we're going to divide that by 1,000, which gives us 0.005 kilograms. Velocity at C, well, what do we think? That's what we're looking for, right? Because we want to know the speed at which the marbles fall into the can. So that's one of our unknowns we're looking for, so let's just leave it as VC, make sure it's squared, and then we want to subtract the initial velocity squared. So we're starting up here at A. What's my velocity up here at A? Well, that's going to be 0, right? Because it says they were dropped from rest. So that will be 0. All right, so it might help. This is our starting point, so point 1. And this here would be our final point, point 2. So now if we have this, what do we think that's going to equal? Well, that is going to equal 0.0025 VC squared. All right, we got that. Now let's do delta VG. Remember, that's mg times h2, or the final h, which in this case would be c, so hc minus the initial height, let's call it ha. Now, before you do any calculations here, we want to set up a reference point. So I am going to make my reference point right here. All right, you can make it wherever you want. You could make it, here if you wanted. You could make it here. Doesn't matter, you just got to measure both of these values from that same point. If we're above that line, it's positive. If we go below the reference line, it's negative. All right, so just keep that in mind. So with that, we're going to have our mass, which is the 0.005, and gravity, 9.81. HC, what is HC going to be? It's right here. That is right on that reference line, right? So that's going to be 0. And then we subtract HA. Well, measured from our reference line, we're going to have this distance here. So that's the 3. So we'll subtract that 3 there. All right, now we get that. And this ends up equaling negative 0.147. All right, so now we've got that. We're going to set it into this equation here. All right, so 0 is going to equal delta t plus delta vg. So that means we're going to have 0 equals the 0.0025 vc squared minus 0.147. Then we can move this over to this side, divide by the 0.0025, and take the square root. And then that gives us a VC value of 7.67. Right, and that's going to be meters per second. So this is the velocity that these little marbles have when they hit this container at C. All right, that was one of our answers, so let's go ahead and circle that one. Let's see what else we need to find. So remember, it says we want to find the speed at which the marbles fall into the can, which that checks that one off. But we also want to find the placement R of the can, and that's this distance right here. Now all we have right now for information, we have the velocity at A because it was at rest at A. We have the velocity at C, and I have these heights. That's all I have. Now, in order to find this distance, it makes sense that I need to know how fast the marble's coming out of this tube, right? I need the velocity at B. I don't have that yet, so we need to find it. So the easiest way to do that is going to be to use potential energy from A to B. All right, so this is going to be the second time we use that. So let's put these in red. So this will be our first point, and this will be our second point. And we can still use this reference line here. That's going to be fine because these values are from that line anyway. So let's just keep that. And let's go ahead and write out our work energy equation. So we're going to have 0 equals our delta T plus delta VG. And this is going to be going from A to B. All right, so if we write it out, we're going to have the 1/2 times the mass times VB squared minus VA squared plus MG HB minus HA. All right, so all we're doing is basically updating our final point, and then this will allow us to get the velocity of B. And then after that, we can use that to find R. So let's go ahead and start filling in these values. So we're going to have 1/2 mass is 0.005. VB is what we're looking for, so just leave it as VB squared. And then minus VA squared. Well, VA was 0 because it was at rest. And then we're going to have plus M, so 0.005. G is 9.81. And then for HB and HA, we're still going to use this same reference line. So this value here is going to be HB, which is 2. And then we're going to use this distance for HA, which is 3. So that'll give me 2 minus 3. All right, so let's calculate that and see what we can get. All right, so that gives us 0.0025 VB squared and then minus 0.04905. So that means we can take this over to here, divide by that mass term there, that 0.0025, and then do the square root to get VB. And that gives us 4.429, and that'll be meters per second. So that's the velocity we have when the marble's coming out of the tube. All right, so we're going to need this to calculate that R value. Now the way we're going to find R is to use kinematics, because if we look at this point, once it comes out of B, this is just like a projectile problem, right? And we're concerned with the x direction. So let's use our x equation from kinematics to find that. Now notice when the marble comes out, the velocity is going to be in the x direction, right? So keep that in mind. So let's write a little note here. We're going to use kinematics to find R. And the equation that we have is x equals x naught plus v naught in the x direction times t plus 1/2 ax t squared. Now obviously some of this cancels out. So ax is going to be 0 because we're not paying attention to any air, wind resistance, anything like that. X0 is going to be 0. because we're going to assume right when it comes out of the tube, that's our starting point. And then x, the final x, is going to be r. Right, so we're going to have r equals the initial velocity in the x direction, which remember we said is this, because it's not coming out with an angle or anything, so that velocity is all in the x direction. So we're going to have 4.429 times t, and there we have that. Okay, well, do you see a problem? We don't have t, right? I gotta have t. So t is what relates the x and the y directions together, right? So now we gotta find that. So we're just gonna look at the y direction now, and then that will give us t. So let's go ahead and let's put this over here. We can use that same equation though. Right here. Actually, let me use the same order I used over on the other one. All right, so we got y equals the initial y plus the initial y velocity times time plus 1/2 ay t squared. Okay, and remember, we're going to measure everything from this point B right here. All right. At least that's what I'm doing on this one. Okay, so with that, y then is going to be that -2. We're going to set that equal to 0. And then the initial y velocity is 0, right, because the marble comes out horizontally. And then we've got a plus 1/2. We got a -9.81 for ay, and then we have t squared. All right. So that gives us 2 equals 4.905. Those negatives cancel, times t squared. So t is 0.639 seconds. Right, so now we have our time. Remember, time relates x and y. So we just take this value and plug it in right there. So r then will be 4.429 times 0.639, which is 2.828 meters. Right, so that's that horizontal distance that the marble travels after it leaves the tube at point P. All right. Hopefully that one made sense. It combined work, energy stuff with kinematics from the very beginning of the class. So hopefully that one makes sense. And I will see y'all next time for another topic.